Yes, greetings of the day to you all. This is Dr. Bindu Madhavi, Professor in Physics, PSCMR CET Vijayawada. Welcome to fourth session of a 3-day faculty development program on moving to master science in technology. A warm good afternoon to an honorable, prolific and inspiring speaker, Dr. Tasim Tajuddin. Sir, on behalf of the organizing members of this program, I welcome you and all the participants who attend today's session on aerosols. These are small particles, huge impacts. Now let me present the agenda of today's session. First, I go with the introduction of the resource person, Dr. Tasim Tajuddin, Assistant Professor in School of Mechanical Engineering, IIT Goa. Then I'll go over some specific things we need to pay attention. After that, we will proceed for presentation by Dr. Tasim Tajuddin, which will be followed by a question and answer chunk. Now, I take the privilege of introducing Dr. Tasim Tajuddin, who is currently working as an assistant professor in School of Mechanical Sciences in Indian Institute of Technology, Goa. Before joining IIT Goa in May 2018, he was working as a postdoctoral research in Indian Institute postdoctoral researcher in Institute of Particle Technology, Friedrich Alexander University, Germany, in the group of Professor Wolfgang Pickott. He worked as a guest scientist from 2015 to 17 in the same group with a fellowship from Alexander von Humboldt Foundation. He is an accomplished researcher with 23 publications in national and international journals to his credit. He presided 2 conferences also. He was awarded a doctoral degree for his work on mass, momentum, and energy transfer in aggregated particulate media in 2013 by the University of Minnesota, USA. He got his master's degree in mechanical engineering from prestigious Indian Institute of Technology, Madras in 2008 and bachelor's degree from National Institute of Technology, Calicut in 2006. Now he is reviewer for some journals also. Aerosol Science and Technology, Nature Scientific Reports, Science of Total Environment, Journal of Aerosol Science, Nanomaterials, Communications Biology, Journal of Geophysical Research, Atmospheres, Journal of Colloid and Interface Science. His main research interest lies in understanding the physics involved in the growth of nanoparticles and improving the characterization of functional and complex nanoparticles. See, this is about today's speaker. So, dear participants, for comfortable virtual learning in this session, let us follow these instructions. Please mute audio and video in your device for avoiding disturbance during the session. Do not share anything on the screen. Avoid unnecessary chat, please. You can post your questions in the chat box. And we also will post feedback link and at the end of the session in the chat box. Now, let me close by wishing you all a delightful and stimulating speech by Dr. Tasim Tajuddin. I welcome Dr. Tasim Tajuddin. Sir, please.
Hi, am I audible? Mr. Tasim.
Yes, sir, you are audible.
It's clear, right?
Yes.
Okay, fine. So I'll start with my presentation. I'll try to share the screen. Is that visible now? Hello?
Yes, sir.
Yeah, okay, fine. Perfect. Okay. So thanks a lot for the introduction, Dr. Bindu. And thanks for this opportunity. And I also thank the first one who was contacting was Dr. Arundhati Reddy from the institute. Okay, so just to start with, I got this option to give a presentation, and I thought it's better to give on a general topic because aerosol is something which I'm deeply involved in. That's my main area of research. So I'm going to talk about like 1 hour into the details of that I'm working on. I don't think that's going to be very fruitful, especially in a webinar kind of a setup. So I'm going to give a brief overview on why aerosols are important, especially with respect to the airborne transmission of COVID. We have heard a lot about aerosols. And once I decided on the topic, I was actually searching for an apt and a succinct topic to give. And this one was from the NASA website, where they talk about aerosols as tiny particles with huge impact. So I think that kind of sets the tone for this talk, as well as so that kind of sets the tone for this talk, as well as give a uh, brief idea about what I am going to discuss today. Right. So let me just move forward. So before I start with the actual presentation on the technical details, I'll give a brief introduction on IIT Goa because we are among the youngest IITs in our country. So it started in 2016, and a lot of us joined in 2018. And so our first batch of undergraduates are graduating out now. Basically, they are graduating out in this COVID semester. And so we have around 600 students and more than 50 faculty members, a good faculty to student ratio. So we are being hosted in our temporary campus by Goa College of Engineering. And so we have set up our hostels for our 640 odd students, plus our academic sections and different buildings in the campus. So we go by the school system, and we have degree programs in computer science, electrical, mechanical, and a new course on math and computing. We have master's program in the traditional branches, plus we are also starting in chemical engineering and material science. Right? So because ours is a new institute, what we are trying to do is, as for research, we are pooling in resources, and we are having a certain team where a lot of faculty members are contributing. So we have a center of excellence in particulates, colloids, and interfaces. And particulates is one where aerosols. Okay, I was told that my screen is not visible. Let me try it again. Is it better now? Is it visible now?
Yes, sir.
Sir, checking.
Visible,
1 minute,
visible.
sir.
Okay, fine.
Yes, sir. It is now
Perfect.
visible.
So,
It
yeah,
is now
so
visible.
just
Okay.
stop me if it happens. And yeah,
Okay, sir.
in the
Okay,
middle of the
sure.
talk, that's fine. Yeah, so we also have, so basically we are pulling in resources for combined research. So we have certain themes that a lot of faculty members in the institute are working in. So particulates, colloids, and interface, where also the aerosol fits in. We also have a center for appropriate technology, wherein we look at local problems. We try to engage in different problems with people around the campus. So that's termed as appropriate technology. We are also starting a center of excellence in combustion research. So we look at the combustion aspects in forms of alternative energy, as well as environmental impacts coming out from that. And just to stop, as I finish this part of the presentation, so I would also like to share a link that's our admissions for our the PhD admissions for all these schools are currently open. Some of them are closed, but especially my department and others are open. So for candidates who are interested in, so I'm just sharing. Uh, if you need any information, you can just go to the website and see more details in there. All right. Okay. So let me just start with the main part of the presentation. So I'm sure most of you would have heard about aerosols. You would have heard what, at least in the last few months, a lot of newspapers and the news articles have used the word aerosols. So I'll introduce what it is and we'll go into the very basics of it. So particulate matter pollution, I think this needs no introduction right now. Always, especially in the winter, we hear a lot about pollution, PM 2.5, PM 10 stuff. And so we'll go a bit more into detail on what this is and what's causing it and what is being done around the world right now. I'm sure most of you would have read about airborne transmission of COVID, the coronavirus, where it's proved, or that's basically probably the main reason that we are having a webinar right now. And I think it was aptly pointed out in today morning's presentation that when there are problems like this, it also is a possibility for opportunities. So it's given us an opportunity to use this e-learning further to have sessions like this where we can have knowledge transfer. So, and we hear a lot about this mask and the importance of using mask in public places. The basic principle for that also comes from the field of aerosol science. Why we use mask and how it's important and stuff also we'll get into details today. And the last part, I'll briefly emphasize on what's being done with respect to climate change. All right. So aerosols play a huge role in localized climate settings and weather patterns, and also global has an impact on global warming as well. So I'll briefly allude to that as well. So I think with just this overview, it's enough to say that although these are tiny, they do have a huge impact. All right. So let's start with aerosols. So what are aerosols? So going by the basic definition in Wikipedia or in a basic aerosol text, you would see that an aerosol is a suspension of fine solid particles, solid or a liquid particles in air or another gas. So basically you have a medium, which is a background gas, be it air, which is the most common, or another gas, and you have suspended particles, be it solid or a droplet. So normally when I introduce this in class and I ask my students, undergraduate students, for have they heard about aerosols? Of course, most of them would give me the example of a deodorant. Of course, the deodorant is a very good example of aerosol. So it has liquid droplets or small particles which are dispersed in air or the gas, right? So aerosol and the suspended particles are called as aerosol particles, or depending on the size, they are called as aerosol nanoparticles. So you have particles and you have it suspended in a background gas. Both these together are called aerosols, and the particles are aerosol particles. I'll try to stick to that definition, but I might use it interchangeably. So I'm just giving a heads up on that. So another example is there are many examples for aerosols. We started the year 2020 with another catastrophe, that was the wildfires in Australia, which is the first of many bad news, which many issues which 2020 brought along with it. So wildfires also release a lot of aerosols into the atmosphere. Then the most common sources right now, or the man-made sources, we have the combustion emissions which come from the exhaust of cars or any for the use for transportation. Transportation and vehicular emissions are among the most prominent sources of air pollution in urban environment. Right? So it's not a new phenomenon, right? Even in the pre-industrial era, so we had aerosols. We have been emitting aerosols into the atmosphere. So ever since we discovered fire, which is among the most prominent discoveries that we've had, it emits smoke which contains unburned carbon, which we call as the soot particles, right? The soot particles are kind of aerosol. They are aerosol nanoparticles. You can see it's an electron micrograph. So to see these particles, you need an electron micrograph. And so this is the electron micrograph of soot particles. So these are not spherical. These are not spheres. They are like clusters of spheres which are clumping together. This we refer to as fractal aggregates because they have a certain structure. This is a particular area by itself. I'm not going into the details. So this is one of the area which is closest to my area of research. So I work on non-spherical aerosol particles, right? So when you talk about nanoparticles, the sizes, I think you would have heard the definition in previous talks, but rule of thumb, the definition says nanoparticle is any particle which has a feature size in the order from 1 to 100 nanometers or like 10 to 100 nanometers. This is just a rough estimate and it's not a hard and fast rule. Even above that, we sometimes refer to as nanoparticles. So one thing to mention right now is that so when you talk about aerosol particles, you normally have the upper limit in a few microns or a micrometers. Anything more than that, it's normally called droplets or like a suspension. So we have a range from a few nanometers ranging to a few micrometers. Anything in between, we refer to as aerosol particles. So there are two main classifications. One of them is anthropogenic, that is a man-made source, and against a natural source. So in this figure on the left side, you have the major natural sources. And on the right side, you have the main man-made sources, right? And in the middle, you have certain electron microscope images of different aerosol particles, which have been imaged using electron microscopy, right? So for the natural sources, you have one of the main one is the sea salt, which is in the atmosphere that comes from the ocean. You have the volcanic eruptions, which can add aerosol particles, wildfires, as I discussed before. The impact of volcanoes can be huge. Like I still remember a few years back, there was a volcanic eruption in Iceland, and it introduced a lot of aerosols into the atmosphere, and a lot of flights had to be cancelled. The air traffic was affected a lot, and it took a few weeks or months to get it back to normal. Another big source is the storms in the desert, or we call it the desert storm, which also introduces a lot of aerosols in the atmosphere. All right, so it's not necessarily a localized phenomena because a lot of these particles can be transferred across far away from the source. So it's not a localized phenomena. These aerosol particles can be taken far off. All right. And on the right side here, you have the main anthropogenic sources. And I think a lot of us can relate to what's in here. It's mainly the combustion sources. And the second one, basically, this is a very pertinent image for our country as well as many developing nations. Uh, the burning of solid fuel and cooking introduce a lot of particles. This is especially important for indoor air pollution. Essentially, we are inhaling a lot of these aerosol particulate matter, and still there is a lot of effort which is being done to reduce the impact or trying to get better at it. So it's becoming so much of a problem that in one of the recent conferences, a study in India showed that even the second generation kids are being affected by the inhalation of these particulate matter. So it is something which requires, hello? Yeah, so there is something which requires a lot of attention from us. Okay, and so then there is another distinction called primary versus secondary aerosols. So whatever we discuss now are primary aerosols. That is, these aerosol particles are particles which are being emitted to the atmosphere. Secondary is when certain chemicals combine with other chemicals and form aerosol particles, and these are called secondary. But most of this talk will stick to primary particles, right? Okay. Yeah. So this is basically a crux of whatever I discussed so far. Before the Industrial Revolution, most of it were related to the natural layers and that we use. But the whole thing changed since the Industrial Revolution. So from then onwards, we basically are looking at the change in physicochemical properties from the combustion generated, especially the combustion generated nanoparticles. So when you talk about combustion nanoparticles, it's not only these which are creating issues, but combustion is also one of the main sources for synthesis of nanoparticles. So there are like very good aspects from the combustion as well. So it's something which we cannot avoid at the moment. At the best, what we can do is we can try to make it better and have better properties. Right? So I think I talked about the scale before. So we define nanoparticles as something with a feature size less than 100 nanometers. So this is a scale I normally have in my presentations. Uh, like it's in nanometers. On the left is like 0.1 nanometer, which is essentially an angstrom. And on the rightmost, it's like 100 million nanometers, which is a tennis ball, right? And our viruses that we talk about comes in a few hundreds of nanometers. So, and within this range is all the nanoparticles that we talk about. These nanopores, I think there was a discussion of nanopore in today's forenoon session presentation. We talk about quantum dots, nanotubes, nanosheets, anything we talk about nanoparticles which come in this range. So I said it's a ballpark, it's a more or less a rule of thumb, because there are also these, we talk about nanofibers, which are really long, which comes in micrometer sizes. But one of the distinction, basically the diameter is again in the nanometer scale, right? So again, from pre-industrial area, we have nanoparticles. So the middle one, this image is of what is called as, what is called as Damascus steel. Damascus steel was very popular in our ancient history for making sword, and so later it was found that after analysis, it was found that the Damascus steel has. Hello.
Sir, please, you continue. Somebody has on the audio. That was
Okay, fine, sir.
You please continue, sir.
Fine. So perfect. Okay. So Damascus steel was found to have carbon nanotubes, and I don't know how many of you are Game of Thrones fans. So this was this was the main inspiration for George R.R. Martin, who came up with the Valerian steel. So Valerian steel is supposed to have been inspired from Damascus steel, which had carbon nanotubes. Then this is one of my favorite examples when I teach the class of nanoparticles. This is something you can look it up. It's called a Lycurgus cup, Lycurgus, and so it's in British Museum, and it was in somewhere in 6 BC, if I remember correct. So the amazing part is that so this has a different color when a light is shown on it, right? So this is like green and red in color. And of course, this is an ancient one, so we can't break it up and see what's in there. But there were some powders which were seen at the bottom of it, which was used for analysis. And it was shown that there were like gold nanoparticles which were embedded in which this comes from a long time back. So it's still, I don't think we believe that our ancestors had a know-how to make nanoparticles, but some of these processes did have an effect and did synthesize nanoparticles, right? And so that was a basic introduction on aerosol particles. So now I'll go more into other pollution aspects, right? So I'm sure you would have heard about what particulate matter is. So especially come November, December, you open the newspaper, open the portals, you see like every day you have articles on the air pollution level in Delhi and NCR region. And a few months later, we just forget about it. The cycle keeps repeating. Delhi is a pretty curious case because there are a lot of factors influencing the pollution level, be it the use of solid fuel for heating purpose, because we don't have centralized or internal heating at home, a lot of us still resort to using firewood for heating outside as well as inside. Then the crop burning, the stubble burning, as the technical word, from the states across New Delhi and the NCR region, which brings in all these particulate matter to the NCR region. And in summer, there is hardly any airflow. So you bring all of these together, the fog, then the vehicular emissions, all of these together, which adds to the issues that Delhi is facing. And we read articles like among the top 25 most polluted cities in the world, in based on the PM 2.5 emissions. We have like 10 of those come from India, or a lot of them come from the Indian subcontinent. Like, so see these numbers in terms of the pollution, only people who are working on that area uh, can actually look at the PM 2.5 and level and say how bad it is or how okay it is. So to avoid that problem, the government came up with something called air quality index. So where you normalize the number and you have a particular number for all the pollutant levels. In addition to that, there's a color scale starting from very low values to pretty high values. Like I think this one refers to hazardous level, which means even for a very healthy person, going outside without a mask is a pretty bad situation. So this has a lot of issues on respiratory aspects. And again, every year we hear these problems and we do some things, but then again it comes back to the same issue again. So we hear a lot about PM 2.5, PM 10. Then PM stands for particulate matter. So 2.5 and 10 here represents a size in micrometers. So what size we'll get into the next slide, right? So to give you a representative scale, so you have this human hair, which is around 50 to 70 microns. And then compared to that, five of the PM10 particles, like particles which are 10 micrometers added together would be the size of a human hair, like the width of a human hair. And even 4 times smaller than them is PM 2.5, which are both by the combustion particles. The PM10 is mainly dust. We call these are coarse particles and these as fine particles in there, right? Okay, so the basic definition is like this. PM 2.5 represents particulate matter, which is basically aerosolized particles with aerodynamic diameter less than 2.5 microns. And for PM10, it's basically the same particulate matter, but slightly larger sizes. So they are particles with diameter less than 10 microns. And so it says there aerodynamic diameter. So because a lot of these particles are not just spheres, and we need something called an equivalent diameter. So it's like you're comparing a cylinder, you're comparing fractal aggregates, you're comparing spheres. So you need a certain scale which compares across shape and size, right? So anytime you refer to PM 2.5 or PM10, you should understand what it is. So that's why I'm going for the basic definition here. So aerodynamic diameter of a particle is equal to the diameter of a sphere. So it's equivalent to a sphere, but that sphere is basically water droplet. All right. So it's equivalent to a water droplet who has the same settling velocity. I'll give you through an example. So imagine that this is your particle. So if you are dropping this in the air, it falls down due to gravity. All right. And you know that as you move, there's a force which is opposing your motion, which is the drag force, which is the reason for we having to spend energy in motion. And in addition, there is also the buoyancy, which you know from Archimedes principle. But buoyancy can be neglected, or it's very small when in the it's a gas and it's not a liquid. So we are talking between the weight of the particle and the drag force. The force balances or equilibrates really fast, and the particle comes down with what we call as the terminal velocity or the settling velocity. So imagine you are dropping a particle, and on the side you are dropping a water droplet. So the size of the water droplet, which has the same settling velocity as the spherical particle, is what is defined as the aerodynamic diameter. And you'll see the aerodynamic diameter used a lot in aerosol science. It is also used for collecting particles, for getting the size of the particle. So when you hear about PM 2.5, PM10, it's basically the aerodynamic diameter that we are discussing in here. All right. So just to reiterate further, it's for any arbitrary particle, it's the diameter of a water droplet. I want to simplify it as a water droplet which has the same settling velocity as the particle that we are considering. Right. So for all this air quality, we have the WHO standards. So for, like I said, PM 2.5 is fine particle, and for the coarse particle is PM 10. So there is 10 microgram, which is an average over the mean. So always we talk about in concentrations. We don't talk about absolute number because they are dispersed in air, and it doesn't make sense to actually talk about certain mass. But if you always talk about in concentration, so this is a mass concentration. That is X amount of mass in 1 meter cube of air. And so we don't talk about a particular instant. We normally go for an average value across the day and an average value across the year. This has to be below a certain level as mandated by the World Health Organization. The World Health Organization also says that so in many places, the accepted level is 35 microgram per meter cube, while they mandate around 10 microgram per meter cube. If it is reduced from 35 and we are able to reduce to 10, we could reduce the air pollution related deaths by around 15%. And in many European cities where the pollution level is at a pretty good level, still it's estimated that the life expectancy is around 9 months lower than if there were no exposure to these particulate matter. So it definitely has an impact. These particles has an impact of mortality as well as life expectancy. So here we talk about the fine particles and the coarse particles, that is PM 2.5 and PM 10. If you have been paying attention, so what are the sources? So like I said before, the main sources is definitely from the combustion, be it solid fuel, the liquid fuel that we use in vehicles, from construction sites, from our industries. So these are the main contributors to the particulate matter. And ambient air pollution is the most important environmental risk factor for mortality worldwide. And if you're wondering what is our contribution to it, you would have seen, or if you look at it right now, you can see a lot of articles where measurements have been done and say that there are clear skies during this time of the COVID lockdown. Basically, as we are staying indoors, the pollution outside caused by anthropogenic sources have reduced, gone to a lower level, and so that air pollution level is at a pretty their quality level is pretty good in most of the cities where it's coming from the anthropogenic sources. So the question is, can we go back to that level? I mean, it's definitely possible, but it takes a lot of effort from our side, and it's not possible to do it overnight because of our dependencies on all these sources, right? And if you look further, so we looked about fine particles and we looked about coarse particles. But in the recent past, maybe last 15, at the most 20 years, we hear a lot about ultra fine particles as well. So these ultra fine particles, if you look at the health effects, you can't read it, but I'm reading it out loud. So PM2, PM 0.1. So by this, you can assume that, or you can guess that PM 0.1 refers to particles whose size is less than 100 nanometers or zero point 0.1 micron, right? So these are linked to diabetes, cancer, and they can travel all the way to olfactory nerves to the brain and cause even cerebral and autonomic dysfunction. So if you look into literature, there are so many papers dealing with the health effects of ultrafine particles, and it shows there is epidemiological evidence that ultrafine particles are can be related to a lot of these especially respiratory and even diseases affecting some part affecting in the brain development. So there has been recent studies also talking about the PM exposure of kids going to school and the effect it has on brain development. As you can guess, the ultrafine particles, the rough definition is sizes or the really small particles whose size is less than 100 nanometers. And I'm just reading out one important sentence from these newspapers. So due to the small size, the ultrafine particles can be inhaled deeply into the lungs, enter the alveoli, which is the last part of our respiratory system, can penetrate biological membranes, it can enable them to pass into the systemic circulation, overcome the placental barriers, even for the neonatal cases, we need to look into it. And finally, it can diffuse into all the organ systems, including the brain and nervous system. So diffusion is an important part here. We'll get to that in a bit. So these are really small particles. So they diffuse. The Brownian motion, which was discovered by. I mean, a lot of you know about the discovery of the Brownian motion. So as these are small, they move around due to the collision between the background molecules, and they can diffuse and they can go further away from their sources. Okay, and so again, going back to the World Health Organization guideline, so the fine particulate matter, we talk in terms of mass per unit volume. So whatever we are measuring is a mass concentration. So we measure in terms of the mass of the fine particle which is available in a certain volume. All right. So all the policies that we make are again for mass concentration so far. So I'll tell you what we think is the issue in here. So this is like a small sketch. Imagine the larger particles are let's say 2.5 micron particles, and the smaller ones are. This is just for a discussion. This is not drawn to scale or number. So the small ones represents ultra fine particles. Let's say they are 10 nanometers or 20 nanometers. So by just counting, you can see that the number of these particles are quite high compared to these larger, at least more than double the number of these larger primary particles. But now, if you look at the mass, the ratio between a larger particle, which we say as 1, and the smaller particle, this is radius 1 cube on radius 2 cube. So if you have, let's say, 1 micrometer, which is 1000 nanometers, and you have the small one is 10 nanometers, the ratio of their radius is 100, while the ratio of their mass becomes 1 million. So you need like 1 million times the small particles compared to the large one to have the same effect on their mass. So what happens is, if you're considering the mass, you don't have any effect of these smaller particles while they're actually present in the atmosphere. So we may be looking at a PM 2.5 number, which is, let's say, under 10 microgram per meter cube, but there are a lot of these ultrafine particles which are present, but they do not have any impact on the mass, but they have a huge impact in the number. So all over the world, aerosol scientists are clamoring, or we are trying to get the policy to go from mass-based distribution to a number-based. That means you also need to have a number concentration of these ultrafine particles. You need to
Sir,
monitor
excuse
the.
me.
Yeah.
Sir, Doctor, uh, your PPT is missing, sir. Can you please share it again?
Okay, sure.
Okay, sir. Thank you, sir.
No. Is it visible now?
Yes, sir.
Okay,
Yes.
perfect. So this slide was done. As in, could you see the slide, or should I go in again?
Just give me a second, sir. Yes, it is okay, sir. It is okay.
Perfect.
Right.
So the main takeaway here is that for ultrafine particles, we need to have a number-based concentration. So, but that again brings about the issue that most of it, these instrumentation for getting this number concentration for these small particles, it's quite expensive. So finding the right sensors to do that is an area of ongoing research. So if anyone is interested in developing sensors, so this is a hot area right now. You have sensors for PM 2.5, PM10, and so for these ultrafine particles or like less than 1 micrometer, you don't have very reliable sensors because of it's very difficult to measure. This is an area to be in right now. Just to add to whatever I've discussed so far. So I'm giving the example of uh, the particle size and distribution. All right. So on the x-axis, you have the nanoparticle or the aerosol particle diameter. On the y-axis, you have concentration. So unlike, let's say, a solid particles that we can measure the sizes, let's say we are buying 1,000 spherical balls for beads from a company, we specify that it has to be one particular size. But when it comes to these nanoparticles, however well you make it, there's always a distribution. So if you want particles in here, I think the peak is around 10, 20, 30, 50 nanometers. So this is in nanometers. 50 nanometers, you have the maximum concentration. So there's always a width. There are particles which are smaller than 50, that are larger than 50. So it's called a polydispersed particle distribution. It's impossible to have particles of only one size, even if you want to make one. So you would always get particles, when you make particles of 50 nanometers, you have particles smaller than this and larger. As you get better at synthesizing it, your distribution comes narrower. Like this will be a narrow distribution than what is being shown here. So this image has three different particle sizes. One which is not visible, which is around, I think, which is around 50 microns. Another one here, which is around 500 nanometers. Another one, which is 50 nanometers. And here, the y-axis is basically for number concentration. So now, if instead of the number, if you were measuring the total surface area available, so the same particles, you are measuring the surface area. So you see the effect is increasing for the larger particles. For the smaller one, you have a very slight effect in the total surface area, right? So this is the area. Now, if you go to measure the volume of these particles, you don't have any effect of these small particles. You have a impact on these larger 500 nanoparticles, and you see the whole volume distribution is main contributions comes from the really large 50. Yeah, it's 50 micron particle. Not, yeah, 5 micron particles in there. All right. So this is the same issue when we go for PM10, PM2.5 measurements. You don't see the effect of these ultrafine particles, which is basically causing the largest or biggest issue to us in terms of illness and respiratory illness and other issues. And there is a need to go into the ultrafine particulate matter when we talk about air pollution aspects. So now I've just compiled the main aspects of ultrafine particulate matter. So here you have an image, the reference is given here, of our respiratory system. For these really large particles, we don't have to worry about, because our nostril, right from our first stage, wherein our hair in the nostrils, they take away the particles, which they take away the particles, the larger particles which come in. The smaller particles go in, like 1 to 5 micrometer particles are separated out in the other part of a respiratory system. And as discussed before, the really small particles go all the way into your alveoli, which can even directly go into our bloodstream. This is basically creating issues for us. And again, how much, what sizes and what shape of particle goes into the human body is an area of a lot of work is going on in that area. So as discussed before, it's a really small particles which can go all the way into our alveoli and go directly even to parts of our brain and even our bloodstream. So high surface area is basically the main reason that nanoparticles are found to be extremely useful. They have a very high surface area per unit volume, and this is also adds to the disadvantages to it once it gets to our body. And they can be deposited. There's a lot of alveolar deposition. I think, this basically enlists a lot of these issues which comes in from these ultrafine particles, which we need to take extreme care of. Right. And so they can enter the circulation, they can go directly to the brain, and they can also transport to other organs in there. Right. So before we end this part on air pollution, there is one particular aspect which I want to discuss further, which is an area which I am getting into right now. It is indoor air pollution. So we discussed, we talk a lot. Okay, we talk a lot on environmental pollution. We talk a lot about the PM 2.5, PM 10. Across the world, there has been a lot of emphasis on indoor air quality, and we are also gradually getting in there. Say we are talking about school-going kids. They are sitting in the classroom for like 6 hours straight. Right in our offices, we spend a lot of hours. Then we go back home. We are basically indoors for most of us based on our job and our current careers. We spend like 90% of our time indoors, right? And hello. Yeah. So indoor air pollution. So we spend a lot of our time, and but also if you look at the air quality, the particulate matter is maybe like 2 to 5 times or even more compared to outside air quality. So this is something we normally we know, like in Delhi we use air purifiers or in places where it's really bad, but this is also an issue in other places where it has to be monitored. Say like I'm sitting in my office right now and I have a printer in my office. The printers, as you print, they also emit particulate matter, which also goes into our body, and this can be in the fine particulate matter range. These are something which we don't care about much, but if you look at indoor air quality, it is something which which we have to continue monitoring properly, and it is something we have to emphasize our work on. So there can be airborne particles from emissions outside or cooking inside. Then also secondary aerosols which can be formed inside the room. Right? And so I don't. Okay. So okay, I haven't given the reference here, but there are recent studies which have related uh, this indoor air pollution and particulate matter level in indoor atmosphere to actually the brain developing in primary school kids. So this is, if you look at the papers on this area coming up in the last 3 4 years, it's an active area of research, and this has to also improve in our country. We also need to look at it more seriously, which brings in the importance of air circulation rate inside a room. So we need to take care about the ventilation rate and to make sure that the ventilation rate is quite high, which improves the air quality inside the room. Is there some noise or is it fine? Okay, fine. Okay, so this was my qualitative analysis or like my discussion on air pollution. So the main takeaway is that the ultrafine particles, so we discussed what PM 2.5, PM 10, PM 0.1 are. So when the whole thing started with the coronavirus, so this is a schematic of it. So basically, it's someone sneezing in a indoor atmosphere. There's someone else who is also in the indoor environment. Okay, there are windows and doors in here. So when it started, there was a lot of emphasis on surface contact. That is, there were a lot of news or research saying that. See, the main issue with the COVID was also that there was not many available research in there. So people are still working on it. The whole world has basically joined hands to work on this area. So we didn't have too much information on this aspect. So the initial report says that it is basically the surface contact which brings in the transmission from one person to the other. So we took care about using hand sanitizers, washing our hands on a regular basis. Then it is also being discussed on droplet transmission. So when I say droplet, the research community discusses droplet as something where the particle size is greater than, let's say, 20 micrometers. All right. And but there was hardly any discussion on aerosol transmission. So aerosol is again aerosol particles less than 5 or a few micrometers. So what happens is, if let's say if someone is sneezing or someone is coughing, so when you cough or a sneeze, you have droplets coming out of your mouth, all right, and that can go far. But also that the big droplets, as they come out, because of gravity, a lot of them actually fall to the ground pretty fast. So this is where the the safe distance with respect to social distancing of 1 meter comes in, saying that most of these droplets actually go to the ground within, let's say, 1 meter or like a 1 meter or like 3 feet. Uh, but there are these small aerosol particles, which is smaller than 5 microns, which can go further because of Brownian motion. We can there be in the air because of ventilation in here. They can be carried from here all the way to the other person or across the room, and they can be carrying the viruses as well. So recently, WHO also started including the aerosol transmission and the use of masks, which was not mandated by WHO guidelines until recently. So this is where the aerosols were not discussed in detail, but this has been found that they can be in the indoor environment for hours, even 1 or 2 hours. So I'm working on such a topic with some of my colleagues from BARC as well as in IIT Bombay. So we are looking at how much for how long these indoor particles can be in an indoor environment given the ventilation rate in there. So what it clearly shows is that this aerosol transmission should be taken into account. And you see, it's not just sneezing or in coughing, even while conversing. Had it not been a webinar, if I were in a room giving a presentation to you, I should have essentially used a mask, because even while presenting, I have aerosol particles coming out of my mouth. There are spreaders, there are super spreaders. There is also a term called super emitters, someone who speaks really loudly, you emit a lot of particles just by conversation. So they can also introduce a lot of these particles into the atmosphere, which might be containing viruses. So this is another work by Bauriba, uh, which was recent. They looked at the analysis of like how far strong sneeze can go into the atmosphere. So this one, the first paper, this is a one which was recently published by Professor Lydia Morowska from Australia. She is one of the pioneers in this field, working on indoor air pollution. And these papers are not too technical, and you can get the reference. You can. It's a very good read on how important or like how bad the aerosol transmission can be for this virus transmission. So this was the image that I show here. It's basically from a work just published 2 years back. So they were working on how bacteria can be transmitted through air, and bacteria and other pathogens can be transmitted through air. So these represent a droplet which is coming out of our mouth. All right. So you have a lot of these pathogens which could be inside the droplet. So as soon as these droplets come out, they start evaporating. So the water, what is shown here is water starting evaporating. Evaporation rate is pretty high for these small droplets, and depending on the humidity and temperature, the evaporation can be high. And in the end, you might be just left with the pathogens inside, or the bacteria viruses inside, plus also some other mucus related not particles, mucus related chemicals which might be left in here except all the water. And this is what you might be directly breathing in. So these are the issues. It's not just the large droplets. There are also the small aerosol particles, aerosol droplets, which can have these pathogens or viruses, and which can be transmitted to others. So then we see, we also know that the mask can reduce your the transmission rates. We look at the aerosol principles behind how mask can be used for such a scenario, right? So now from this, I basically wanted to show that how from these droplets, you can actually even inhale directly the bacteria or the viruses which come out along with these droplets, mainly as you sneeze or if you cough or even during a normal conversation. So I'll be discussing quickly on the particulate matter filtration. The same principle is basically used in microscope. Basically used in the mask. So this is a microscopic image of what is the filter typically used in a mask. All right. So when we think about filtration, normally we tend to think that it's a sieving process. So that means there are holes, and these holes, and the particles can only go through these holes. The rest everything else is like filtered out. Similar to the sieve that we use at home while cooking. Sometimes we use sieves to remove particles. Or people who know from the construction side, we have a sieve to get only the fine sand. So, but this is not exactly a sieving process. So, what you see here is like fibers which are connected together. You can think about something like which is in your shirt or your clothes. You have fibers which can form latitudes and longitudes. And they are the ones which are used in the mask. The working principle we'll get to in a bit. So it's quite relevant as this is what is essentially being used in surgical masks and N95 masks. The mode of filtration and the concepts are the same. And the main question is what size of the particles can be captured. So this image is also this particulate matter, which are basically captured onto these filters, these fibrous filters. Many of these form the filter whose image is shown in here. All right, this is a microscope. This is the microscopic image of, if you guys look at a mask under the microscope, this is what you would be seeing. So I'll try to share a video. Let me know if the audio is visible. Is the audio available?
Sir, excuse me, sir.
Yeah.
If this video is with audio, that is not audible to us, sir.
Okay, fine. So that's fine. I think I'll give you the reference later. I'll go back to the next presentation. I'll go to the next slide. I'm explaining this the phenomena there. Just give me a moment. Yeah. Is the slide visible now?
Yes, sir.
Okay, perfect. So essentially, I'll provide the link. Probably you can take it from the slide as well. But that's freely available, and it's available in YouTube. You can look at it. So basically, what I'm trying to say is that it's not a sieving process where it's a hole and the particles larger than the hole are being captured, but there are different mechanisms which are used for filtration. This is a very basic. I'm not going into the details. So the main mechanism, one of them is diffusion. Diffusion, I know. I mean, most of you should might be knowing, but I'll give a brief overview. So diffusion is basically because of the very small size of the particles. They have a zigzag motion because of collision between the background molecules. And so you have this, which is a cross section of a fiber. If you look at the cross section, it's a cylinder, so it has to be a circle. So as particles move, they move in a zigzag manner, and the small particles come and collide with the fibers and they stick there. Next is interception. So that is because of the size, as they come near the fiber, they get attached to the particles. So interception is for large particles, the diffusion is for really small nanoparticles. Then there is something called impaction. So impaction is due to the effect of inertia. So most of you can relate with me when you say if you are traveling in a bus or in a car, and suddenly when there is a brake applied, I mean the vehicle comes to a stop, but you move a bit more. That's because of the inertia of your body. Similarly, for particles, as the air comes in, the red line basically represents how schematic of how the air goes around the filter. For a particle which comes in through, even though the air moves immediately across the fiber, it would have some inertia that it will not move along with the air. It will continue the motion in a straight line away from the air. So this also can cause the particles to collide with the fiber. They get attracted. Then if the particles are charged and the fiber is also charged, you'll see if you look at the mask, many companies would be advertising advertising now saying that there's electret filtration or some of the masks have like electrostatic charge that can also help in um, filtering out a lot of these particles. Okay, so this is a cross section again. This shows different mechanisms. I don't want to go into the details, but the main takeaway should be that there are different processes or mechanisms by which particles can be filtered out, and it is not effectively, essentially a sieving process. I want to draw your attention to this particular slide. This is this particular graph, which is pretty important in here. So on the y-axis or the x-axis, you have the particle diameter, which is in micrometers. So 0.01 means it's 10 nanometers and all the way to 10 microns in here. And on the y-axis, you have the collection efficiency. And for really small particles in the nanometer range, so the collection efficiency is mainly by diffusion. That means all the particles are basically filtered out by diffusion. All right. So you measure, there are ways of measuring the filtration efficiency. And from this experiment, this shows that diffusion is the main or the main filtration mechanism for really small particles. So interception and impaction, they are negligible for really small particles, and as the particle size grows, this adds to the filtration efficiency. Then there is gravitational settling, which is important only for really large particles. This graph here, this is a total collection efficiency for various sizes here. All right. And do you see it's maximum for really small particles, then the filtration efficiency goes down. It keeps increasing until it gets to 100% efficiency. So this size here, where the filtration efficiency is minimum, this is around 0.3 micrometers or 300 nanometers. And guess where what the size of COVID is? The COVID or the coronavirus has size around 200 nanometers, which comes around in here. So for the normal fibrous filtration, the issues with virus particles is that they fall in the range where the filtration efficiency of all these fibrous filters are at a minimum, right? So this is why we need to we need to look more specific into those. That's why we talk about multiple layers of these fibers, which can increase the efficiency and things like that. All right. And so this is again a microscopic image of nano PTFE membrane, which is used for fibrous filter. You can see layers of these cylindrical filters which are woven together. These are basically how the mask filter would look like. And this is a small comparison of the sizes of diameter of that particular one. This is from a website I've given here, and they've compared it against the sizes of typical particles that you see in here, right? On the right, you have the diesel exhaust. Like these are nanoparticles coming from a diesel exhaust. These are the typical shapes, and the sizes are in nanometers. This is what comes out of an exhaust. And this figure basically shows a schematic of how these particles, once they go in our body, it shows the larger particles which are taken out due to inertial impaction, which doesn't go all the way into the lungs. The small particles go in, and fine particles are basically filtered out in the next region, and the really small ones can diffuse all the way into the lungs. The really small ones could still diffuse to the walls here, but a small part of it can go all the way into the alveoli, even get part into our bloodstream. All right. So I'm basically the same image that I showed in here before. So this is the penetration window. That means the particles of this size from 200 to 500, 600 nanometers, the filtration efficiency is low for a single fiber filter. And this we need to take care about when we are using masks. All right. So when we talk about an N95 or N99 mask, what it means is that it was already there. It's like an anti-pollution mask, which possesses 95% and 99% filtration efficiency. That means the efficiency is around 95% or 99% when you talk about 300 nanometer particles. So if you have 300 nanometer particles, 95% or 99% of them are filtered out by these masks. Still, it's not 100%. So because if it's 95% for 300 nanometers, that means efficiency is higher for the particles which are smaller and particles which are larger. So it's only For these particles of zero point 0.3 micron, the filtration efficiency is 95% or 99% at this particular sizing. All right. So this is a schematic of, you see, when you make a mask, when there are companies making masks, there are a lot of things that they need to take care of. When someone says N95, they have to be absolutely sure that 95% of the particles of 300 nanometers is basically filtered out. There was also in the news that a lot of the PPE which is coming out from Chinese companies were defect. That means it would let in particles of this particular size more than what they claim to be. So this is a very new paper where it's an interesting paper because what they did was they used many homemade fibers, like many homemade clothes. They made fibers out of socks, different clothes which are available at home. They made masks and they try to look at the efficiency. So so typically what is done is there is a aerosol particle generator which is made of sodium chloride or common salt, which you can fine tune so that you get particles of 300 nanometers coming out from this source and which is injected into this aerosol mixing chamber. So inside here you have particles mainly of 300 nanometers, and you have your mask of certain size or the mask material which you keep it in this particular specimen. Then you have um, aerosol instruments which can measure the concentration of particles before and after the filter. So once you measure the concentration before and after the filter, you calculate the efficiency. What's the percentage of particle which goes beyond the mask compared to what is the percentage of particle which is coming into the mask. So you divide it and you get the filtration. This is what all the companies would have set up something like this to measure the filtration efficiency of the mask. So anything, so beyond this filtration efficiency, you also have tests like breathability. It's an interesting read. If you go into what are the requirements for a proper mask, so you need to prove that for sodium chloride particles, which is essentially for 300 nanometer particles, you have to calculate what is efficiency. Then you have to check what is the pressure drop. That means if the pressure drop should be low enough, if the pressure drop is high, that means it would have breathability issues. This is the same reason why if you have 2, 3 masks put together, it's dangerous for you because you can't breathe. So breathability is a huge factor, and then also this filtration efficiency is an important factor when you have to consider when you make the mask. So once you hear about N95, N99 and stuff, this is the basic principle which goes into what represents N95. So the 300 nanometer particle or the zero point 0.3 micron particle is an important aspect here, which by now I think you should appreciate the fact that it's because it's the size for which the filtration efficiency can be the lowest. Okay, let me reiterate that fact again. Okay, so that was a basic overview of the airborne transmission and mass during this COVID time. So I wouldn't, this is a small one on, I think I'm already getting close to 1 hour. So this is on aerosols and impact on climate change. This is an area which I have both the filtration aspect and air pollution aspects I have experience working on, but climate change is something which I'm getting into. It's not something which I've been actively working on. I think all of us are familiar with global warming, climate change, and things. So the impact of aerosols on climate change is something where active research is going on. Because in addition to these gases, aerosols, they reflect and absorb radiation from the sun. So as they reflect radiation from the sun, that means lesser amount of radiation goes to the Earth's surface. They can result in the cooling of the surface. And in large concentration, they can scatter light, which prevents the direct beam of the sunlight reaching the surface. What it means is there are some particles which can absorb, some aerosol particles which can absorb sunlight, like the soot and the black carbon. That means they can increase the temperature of the surface, while the main other aerosols which reflects and scatters, which can result in cooling. So the overall effect of the aerosols on the temperature would depend on the concentration of these particles and these properties, which is not a simple thing to calculate. So the overall effect of the aerosols and their impact on climate is something which is an ongoing area of research. In addition, the cloud formation. The cloud normally starts with a single seed of particles. So there is a single particle, dust particle, an aerosol particle, over which water vapor condenses and forms a cloud that we see. So the properties of the clouds can be different depending on the kind of aerosol particles available. So as an indirect effect, the aerosols can affect the properties of the clouds, which in turn can affect the climate change. Right? So black carbon or the soot, which is in a chimney. So this is from an image from the website I was talking initially, which talked about aerosols, tiny particles, and big impacts. And so this shows that these black carbon can result in atmospheric heating. At the same time, it can result in surface cooling. So it's a pretty complex research problem. There are a lot of research groups working in it, and it's, as I said, it's a very complex problem. And this is something from NCAP Coalesce. So NCAP is National Carbonaceous Aerosol Program. I think this started in 2016. This is coordinated by Professor Chandra Venkatraman of IIT Bombay. This is a huge project from the Ministry of Environment, Forest and Climate Change in India. So it is a very collaborative effort which combines the effort of more than 10 different universities and research institutes in India. You can look at the website. It's called Coalesce. Coalition is a term used for when two particles come together and form a larger aerosol particle. So you can look at more details in there. It's an area of ongoing research where there's a lot of effort happening in Indian side as well. So they are doing a multi-year model. So you look at aerosols in the atmosphere, and you look at what is the effect of aerosols in India, that's having an effect on the climate change and the weather patterns and also the rainfalls in India. This slide summarizes it. I think some part of the cloud or some clouds basically formed when there are a lot of aerosol particles. In those times when where there are more aerosol particles, the clouds are with a reduced water content, which has an effect on the rainfall. Particles where the water content is pretty high, this can also reflect the particles with lower water content can also reflect more sunlight, but here the more sunlight is absorbed or goes down, and this can also create more rain compared to clouds which are formed with a lot of aerosol particles around it. So, in a nutshell, what I want to say is that aerosol also has a huge impact on climate change and weather patterns, which we as a nation as well is looking more into details. And I would encourage you to read more about it. And you can go into the NCAP Coalesce program, which also has like the scientific aspects written in a much simplified manner for us to understand on the kind of research which is happening in there, right? Before I summarize, one critical aspect of the aerosol particles is that most of the instrumentation which comes along with is really expensive. This is the reason why it's not very uh, commonly available. So one area which is there's a lot of scope for improvement is the sensors which comes along with it. So you have sensors for measuring this aerosol concentration. This is an area if you are interested in instrumentation development or sensors. This is a huge area where we can make a huge impact as well with respect to the research aspects. So just to summarize, so we talked about aerosols, aerosol particles. We talked about the impact on particulate matter on air pollution. We talked about what particulate matters are, 2.5 PM10, and a special focus on ultrafine particles. Then a basic overview we did on airborne transmission, how the droplets or how whatever is coming from our respiratory system can be a source of transmitting virus, bacteria, or other pathogens. So the aerosol physics basically determines the use of mass for filtration. And so that's basically the reason why we are also using mask, which can help us help in reducing our exposure to aerosol particles or aerosol droplets. And there's a very brief overview on like how it is affecting climate change. That's because of the properties of the particles. They can scatter, reflect, or absorb solar radiation. And in the long run, it can also affect our weather patterns. So I think I did enough to show that although these are really tiny particles, they do make a huge impact. And these are the main areas or applications that I could find in the time frame for this presentation. I hope I was able to get across this message to you. I would like to thank you for intently listening to my presentation. And if you have any questions, I think I can answer a few here. But if you have more related to it, feel free to send me an email in my official email account, and I'll be glad to answer questions. I think I'll take a few minutes to answer your questions in here. I think that's all I have for now in terms of presentation.
Okay, sir. Thank you. Thank you very much, sir. We have in the chat box three questions. Sir,
Okay.
which one is easy for you, sir? Will you go through the chat box, sir, or shall I read
Uh,
it for you?
you can read. I'll try to find it here as well.
Okay, okay. Sir, at 4:39, we have a question from Kalpana Kannan, sir. Even
For
here at 4:43 also, just
439. Okay. Uh, we get very diverse environments. So what kind of mask should we use? Are surgical masks only the effective ones? Will cloth masks of certain specification be equally effective? Okay, I think that's a very pertinent question, and I think I would urge you to read if you are interested in reading that paper that I was referring in here. So the main aspect is depending on what kind of material you use. Uh, the important part is in what is the aerosol filtration efficiency. Of course, the 95 also comes with like certain risk that is for these particular, let's say the virus, maybe only 96-97% can be filtered out. But what we are essentially trying to do with the mask is we are trying to reduce our exposure. We are reducing the probability of getting us infected. The most important aspect of mask is that, see, if I am wearing mask, if I sneeze or if I cough, the probability of a large particle coming out of me is like absolutely minimal. So essentially, it's a two-way problem. So it doesn't help like if only a few of us wear masks. It will be really successful. I think there's a lot of community level help that is required to prevent this overall corona transmission. So if all of us wear masks, so basically if two of us are in the same room, if I wear mask and you wear mask, so we are basically reducing the probability further down. And again, the continuous use of mask, it is something I think again we do not feel too comfortable wearing masks all the time. And you should, if it's a throwaway mask, you should make extreme care that you take out the mask and you do not use it further. And if you are indoors by yourself, I think you are safer. Like you don't need to wear mask per se. I think it's completely fine in like having a good mask from um, a reliable source that if you are going to wear for it. So if you are asking the risk with the continuous use of face mask, I don't think I am the right person to give a correct answer right now. I think there are a lot of experts on these indoor air who are actually working on this. And to be very honest, I can't give a very if I give an answer, I don't think it will be very reliable enough. So I'm avoiding that. But I would definitely recommend, like, if more people start wearing it, it can definitely affect. Add on to it, see, there is another important problem with the way we use a mask and be it a gloves as well. So we are not used to wearing it. So we see a lot of us actually wear mask and we touch the outer part of the mask with our hand, which is also not the right way to do because there will be a lot of issues. There will be a lot of these pathogens which are trapped by the mask. If we touch it with our hands, we are basically transferring it in our hands, which and we are introducing the risk in here. So we have to use mask and we have to use it properly. We have to use it wisely. I think that's my comment in there.
sir. Sir, there is another question at 4 hours 2 minutes by
For
Lenin
two,
Babu. I mean 4 o'clock.
okay.
4 o'clock.
Why?
Lenin Babu.
Lenin Babu. Okay. Okay, major applications of aerosols in nanotechnology. Okay, so it's a more generic one. So applications, as in, say, you can basically design the diameter of these fibers. You can design something like the porosity, which would increase the filtration. That is one. Plus, I talked about the combustion aspect. So combustion is used as a form of synthesizing nanoparticles. So you can synthesize it in air, that is, you synthesize it in the fire. Like Titania is the best example, which is it's $1 billion industry actually, Titania, because it comes in a lot of these face cream, like face creams. And so you synthesize titanium in a flame. So synthesizing nanoparticles in the gas phase or the aerosol is the best example that I can give right now in terms of the application. Then you saw the aerosol physics being used in how we use a mask, or like how mask can be, the filters can be synthesized. Then I think there's a lot of crowd on physics and chemistry, right? So atmospheric chemistry, atmospheric aerosol chemistry is also an area by itself, because I didn't speak about secondary aerosols. Aerosols are formed in the atmosphere where a lot of chemistry is being involved. So that is another application from the aerosol sides. Anything else? I think that's what I have to add now on that question.
Yes, sir. Yes, sir. But at last, just before
Okay.
5 minutes, we have number of questions regarding using masks. I mean, social distancing, which are related to COVID-19 situation, sir. But I have
Yeah.
a question from our YouTube channel, sir. I'll read it for you,
Okay.
sir.
Perfect.
Uh,
Okay.
See, one question is bio aerosols are virus and bacteria? Question mark. That means that I think they want to know that are these virus and bacteria are called bioaerosols?
Yeah, I think to an extent I can answer. Yeah, that's the same. So bioaerosols is basically anything like the pathogens and stuff which comes out as aerosol. That's what is referred to as bioaerosols.
Okay, okay, sir. Next question is, have you taken any research work on this coronavirus? That is,
Uh,
any physics or chemistry related properties?
chemistry is not something I have a lot of expertise in, so I didn't want to get in there. So, like I mentioned, what I'm working on was like it is a research led in by a colleague of mine in BRC and another professor in IIT Bombay. So, let's say we are in an indoor environment, and if someone is sneezing or coughing, so there is a certain amount of particle and size distribution which comes out. And if you have the ventilation, proper ventilation or lesser ventilation or even a large ventilation, it would be interesting to see, like if I cough and leave the room, if someone comes into the room after, let's say, n number of minutes, is he or she is still susceptible to have a transmission? So these are the things. See, the main issue with COVID or Corona is that it happened so fast now, and we don't have answers to most of the questions. We are anything that we look into. These are answers we are finding out on the fly. There are not too many answers to it. So these are the main topics I'm working on right now. And as to chemistry, no. But and I should admit that if you look into papers which comes out right now, there are a number of papers. Different groups are working on it. Only time will tell like how many of these are effective and how many we can actually use in for policy making. But one thing is clear, like from whatever I've read and understood, aerosol transmission is a thing, and mask is very important aspect to go as far as to reduce the amount of transmission happening in there. I mean, there has to be help from the community side, otherwise this is going to just keep on increasing.
Okay,
Did
sir.
I answer that?
Shall I go for next question, sir?
Please, please.
Uh, we all know about massive incident at Chernobyl. Very large amount of radioactive aerosols were ejected. Could you please
Uh-huh.
tell us the effects of radioactive aerosols?
Oh, super. Very nice one. Because see, radioactive aerosols is an area, research area by itself. Like if you look at BARC, there are a number of groups. There is at least two groups who are working on radioactive aerosols. So the main issue with radioactive aerosols is that you can't do too many experimental research in there. You can't play with radioactive aerosols. And very recently, I think a couple of months back, uh, there was still a paper from the Fukushima incident where they are still measuring the aerosols which is coming from these radioactive sources. I don't have the expertise right now to go more into detail on this, but one thing I can add is they still work is mainly done in terms of this fractal aggregates. So they don't normally come as spherical particles. There are these again come as fractal aggregates, and they can again be dispersed in the atmosphere, and they can be carried further, and they can go further away from the source, just like the principles of normal aerosol that we talked about in here. But the main difference is that at the initial stage, when it comes up, the concentration is really high, and it gets diluted as it goes further away from this. That is another area where researchers are working on with respect to radioactive aerosols. I think if you follow the research from BARC, you'll be able to find a lot more work on that.
Okay. Um, there is another question from Mahadevan, Raghavendran Mahadevan. A lot of us use deodorant and scents. These are aerosols. Obviously, we breathe this. So, can we conclude that these deodorants are not advisable?
That's a tricky question to answer. Say, like, if I say from my personal experience, see, I was someone, see, if you especially look into indoor air pollution, you can see the impact of having like combustion sources inside your home. So I was someone who used to like this incense sticks. I used to have it like because I love the smell. I used to have it at my home very often. But now I try to avoid it because I know for sure that it adds pollutants to my home, and it's not good for me. So similarly, deodorant, yes, of course, it can add to. I mean, you're smelling basically chemicals in there. In that way, I know friends who don't use this deodorant; they just uh, use something else in there. Uh, uh, Let me just think. I don't see the concentration. Maybe it's obviously not too good if you have this air odorizer and then you have it all over the room and you keep smelling it. That's definitely bad. In small concentrations, it may not be that bad, is how I can put it. Along with the technical advancement, there are so many things that we use, which we look into the details. It is definitely not too good for us, but we still keep using it. It's very difficult for us to go away from all this. I think
Okay.
there's one question that again from Lenin Babu. I think at 3:55, I would like to answer that.
Yes,
He
yes.
asked, were aerosols used in manufacturing medicines? That is it helpful to reduce the impact of air pollution? There are some areas, especially like if you look at the air pollution which comes in from combustion, okay, there is an area where you can add particles to the fuel, whereby you increase the efficiency of fuel combustion. You reduce the amount of soot particles which comes out. So you increase the efficiency of the fuel combustion. So in a way, you reduce the amount of soot particles coming out. So that's also another area which I can see that can be used. Again, if you talk about environmental pollution, the filtration, there's something called a baghouse filter that can be used in all these. So you have resources to filter out the exhaust coming out from our industries. So if we are able to follow the timely policies which come up in that aspect, then we definitely can reduce the impact that we have. So when we go further away from it, when we don't resort to or, uh, obeying the policies or getting used to these policies, that when this is again detrimental to the environment. We have ways to do it better. Whether we are doing it is the more important question. Yes, please go.
Okay. Yes, sir. Here I can see another question. What are the major applications of aerosols in nanotechnology?
So, like I mentioned, it's mainly used for nanoparticle synthesis. Like if you have, so there are two main aspects. One is colloidal synthesis. Other one is the aerosol synthesis. Colloidal synthesis is when you synthesize nanoparticles, like wet chemistry that you, I mean, you not wet chemistry, you synthesize nanoparticles in a liquid, And aerosols basically are synthesizing in a gas phase. In liquid phase, in order to keep them from combining with each other, you have surfactant, so the purity is less. While in synthesizing nanoparticles in the aerosol side, you can synthesize particles which have a larger purity. Then you can have dopants, you can add different particles, you can have multiple component particles coming in. You can dope particles with different other elements. So there are advantages to synthesizing in the aerosol side. Thus, I would say is one of the most important application of aerosols in the nanoparticle side or nanotechnology side.
Okay, sir. At the last in the chat box, I just have seen one question, sir. Please try to answer that. By Krishna Raja, COVID-19 aerosol transmission route and 2 meters safe distance. Advice is 2 meters safe.
Yes, so the 2 meters, I think the 1 meter, the 2 meter safe basically comes from the droplets. See, if you have mask, then 1 2 meters should be very safe for you. The moment you don't have, like in an indoor atmosphere, 2 meters, within 2 meters, I think it's a very less probability that droplet. When I say droplet, something which is larger than 20 microns or even larger, they fall to the ground in a matter of seconds. It doesn't go beyond, let's say, a few meters. 2 meters in this aspect. But these small aerosols, again, the main takeaway from this is that the small aerosols, which are smaller than a few microns, which are in the nanometer, which could still carry viruses, which we don't have a very clear idea about, and which we don't have very clear idea about. They could have this could have this virus, and there is still a chance that you could get it. But with mask, with a safe distance, you are basically reducing the probability of it happening. Again, I should say that my expertise is in aerosol, and you should read more about it and go for the right sources. And but definitely keep safe distance. Using mask is the right way based on interaction with all these indoor aerosol experts. But this is definitely a good way to go about it.
Okay, sir. Thank you. I might have missed many questions in the chat box, sir. Shall we ask them to post them into your email, sir?
Yeah, so not many because I won't be able to answer all. If you give enough time, then I might be able to. But if you have anything which is not discussed here, feel free to. If you have any more, if you want any more information from aerosols as well, so please feel free to do that.
Okay, okay. Sir, can you please type your email ID in the chat box?
Fine. So yeah, so I have it in here. Fine.
Okay, okay, sir. Thank you. See, somebody's video is on. Yes, I don't know who he is. He is sharing his screen.
Okay.
Dear sir, please switch off your video. Okay. Uh, we had a good session, sir. Thank you, Dr. Tasim Tajuddin. Your years of research, depth of subject, and your ability to present the subject in such an interesting way has produced an interest in aerosols. You have taken us to the world of aerosols, sir. Really. I was just imagining myself in the sea of small particles. I personally plan to learn more about these aerosols. Anyhow, we are all thankful and grateful for the time and effort you have taken to share your thoughts and work on these aerosols. Thank you, sir. Thank you for a wonderful presentation. And I hope you will visit us again, sir.
Yeah, definitely. And thanks a lot for listening and for this webinar platform. I hope I was able to at least uh, give something about aerosol, at least introduce that topic to many of you.
Thank you, sir. Thank you very much. That you have made our evening today, sir. this fourth session of this faculty development has become a memorable session for this faculty development program. So thank you very much, sir.
Thanks a lot.
Thank you,
Yeah.
thank you, sir. Dear participants, tomorrow we'll start a fifth session of this 3-day faculty development program exactly at 10:30. Okay, thank you all. You can leave the platform.